Hey guys, welcome to another lecture from EcoPoint. In this series of lectures, I'm going to today talk about composite functions. It's a very essential topic in mathematics. It's very essential for you if you are from economics background because many times we use transformations in economics, right? So you should be thorough with the concept, definition, the domain analysis when it comes to composition, the range analysis when it comes to composition of two functions. So let's get started. The first thing that I would like to do here is to quickly recap the definition of a function. So when we say f is a function from a to b, what do we mean? We mean that for every x belonging to a, there exists a unique, one and only one, unique y belonging to b such that the expression fx will be equal to y. Right? So for every x, we have a unique y. Now, when it comes to composition, what is the meaning of composition? Suppose you have a scenario that you have two functions and they have something common. Common as in, suppose g is a function from a to b and f is a function from b to c. So suppose the scenario looks like g is a function which is going from a to b, f is a mapping that is going from b to c. So what you realize is that this b set is common to both. So which means there has to be a way in which I can move directly from A to C because I have a common link in between. And this scenario is the scenario for composition. There are two types of compositions available to you which you can create. One is f of g and the other is g of f. Both are different and understand that conceptually. When we say f of g is the composition f of g of x, and input x is basically, it basically means f of gx, f of gx. In case you are talking about g of f of x, you are basically talking about g of fx. So these two are very different things. See, what's happening here is you are applying f on gx. So gx has to be in the domain of f. What you're doing here is you're applying g on fx. That means fx has to be in the domain of g. So that is what is composition. Now let's see what I have given to you, the scenario that I have provided to you. Here, if I take an x in A, apply g on it, I'm gonna get gx. And now this gx is in B, and hence I can apply f on it, and hence I will get f of gx. So what is the composition that you see from here? You see that A to C, the composition that is getting constructed is fgx. So f of g. The composition here is f of g. G of f will be very different. In case we swap f and g, in the definition, the way we are defining or the way we are constructing it, if we interchange the position of g and h, then g and f, then we can get g of f. So from here, it must be very clear to you that commutativity is not something that gets satisfied by the composition. So g of f is not equal to f of g. Always remember that. This is a key point to remember. The next thing that you must understand here is the domain for any composition. So suppose I'm taking the scenario that I've given to you. So I'm looking at f of g. So when you talk about domain, you are talking about the x's. You're talking about x's, right? So what kind of x can I take for f of g for this function so that I get a meaningful result? Always remember, what's happening here is you have an x which generates gx, and once gx is generated, you are able to generate fx. So what kind of x do you require? You require an x that can generate gx. That means it must be in the domain of g. How do I come to fgx? By applying f. How will I apply f? Only in case gx is in the domain of f. So you do have another condition that gx has to be in the domain of f. And that's how you can find the domain of f of g. Sometimes it will not really make any difference. You'll be able to figure out if the domain of g, you just figure out f of g, you just calculate that, and whatever x or y will are part of your domain. But sometimes it might be different. So let me just give you examples here. Let's start with a very simple example. Let's take basic function fx equals to x square plus 1. Very simple quadratic, right? Suppose this is your fx and suppose gx is equal to log x. Always remember, in economics especially, we take a lot of logarithmic transformations. So that's what you are doing in general. You have log x is gx and fx is x square plus 1. Then in case I take g of f, then I'll be taking log transformation. But here if I want to find out f of g, so that is f of gx. This is basically saying that instead of the input x, your input should be log x. So this becomes log x square plus 1. Now, what I was trying to make a point here when I was giving you this domain is that, tell me something. Can I take log x for all x, for all real numbers? The answer is no. Log x is only possible for x which is strictly greater than 0. So for those x's which are strictly greater than 0, I can take log x and then I can apply f on that. But the basic condition is the condition that x has to be greater than 0. And where are we getting that condition from? Not from the domain of f, but from the domain of g. So gx is log x only valid when x is greater than 0. Okay, that's the domain of g. So x is in the domain of g, and f, for f, input is log x, which belongs to R. So domain of f is actually R. All right. So which is true for x greater than 0 because it will give you a real number only. Now combining the two, you get that the total domain has to be, if somebody is asking you what is the domain of f of g, the answer is it has to be all the x's in R such that x is greater than 0. You can also say it is open 0 to infinity, or it is R plus plus anything. You can write down anything. All right. So this is how you have taken care of. You have taken care of the domain. Now let's take an intermediate level of example. So let's bring denominator. So let's take fx as 1 upon x square minus 1. And let's take gx. Let's take a function gx where we have some restriction. So let's take a square root. It is x plus 2. Let's find f of gx and its domain. So how will we do that? We will, to find f of gx is very simple. We just have to do f gx. So which means that wherever you had x, now you will have gx in the expression for f. So it is going to be this, right? Now you get 1 upon gx square means x plus 2 minus 1. So it is 1 upon x plus 1, right? 1 upon x plus 1. If you find this expression, your answer will be that x should not be equal to minus 1 because that makes your denominator 0, right? So is it that my domain has to be this? Just this? Well, so what you have just realized from here is the condition that gx should belong to domain of f. For gx to belong to the domain of f, it basically means that square root of x plus 2 should not be equal to 1. Because when it is 1, square root, when basically, so if you look at the function f, the restriction on the domain is input square should not be equal to 1. So what is your input this time? It's gx. Gx square should not be equal to 1, right? So gx square is x plus 2 should not be equal to 1. In other words, x should not be equal to minus 1. This is exactly what you got from here. So is it the only restriction for the domain of f of g? Well, you have to consider domain of g also. See, because you get x, then you generate gx, and then when you apply f, you get fgx. So you need to have the x's that can produce gx. Once gx is produced, then only you can apply f on it, right? So therefore, you have to have another condition. Let's see whether that condition gives me something extra or not. But yeah, the condition is that x should be in the domain of G. And the domain of G has one restriction. The domain of G is basically its square root of x plus 2. So x plus 2 should be greater than or equal to 0. That means x should be greater than or equal to minus 2. So if I combine these two things on the number line, if you see, you have 0 here, say minus 1 here, minus 2 here. Everything more than minus 2 is all right. But we just realized x cannot be equal to minus 1. So it is minus 2 to infinity, the intersection of the two, that is the common x's, except for minus 1. Or what you can say is, in terms of number line intervals, if you want to write, closed at minus 1, open till 1, open at 1, union, open at minus 1, union minus 1 to infinity, again open. So this gives you the domain of f of g. And what I just taught you, the two conditions that you have to take care of, always keep that in mind. There are two conditions. Remember, x should belong to the domain of G when we are talking about f of G. If you have a question where you have G of f, please, things will be opposite. Use your logic. Number two, your Gx, because you have to create fgx. Gx has to be in the domain of f. All right. Now let's finally take one example of a little bit of difficult level that could be asked in, one of the difficult entrances for that matter. So suppose your fx is e to the power minus x. Let's bring in e here. And gx is x upon x square plus 1. So we have denominator here, okay? And let's find f of g and its domain. So the first thing first, let's find f of g. So for f of gx, that is f of gx, so it becomes e to the power minus gx. So it is e to the power minus x upon x square plus 1. All right. Now let's talk about the domain of f of gx. So for domain, there are two conditions. Number one, x should belong to the domain of G. And number two, gx should belong to domain of f. So let's take the first condition. X belongs to domain of G. So do we have any restriction on x? Well, gx is x upon x square plus 1. So the only problem we could have had is x square should not be equal to minus 1. Well, that is never the case. X square plus 1 is always positive. X square plus 1, in fact, is strictly positive. So we can say that x square plus 1 is strictly greater than 0, can never be equal to 0. So we don't have any problem here. So what we have is x belongs to R here. And gx should be in the domain of f. Fx is e to the power minus x. So the condition is that input should be a real number. Well, gx is a real number. No matter what x you put, gx is, whether it's negative or positive, you will get a real number. Real input, real output. So gx is a real number. And therefore, if you combine the two, there is no restriction actually. These were difficult functions to look at, but there is no restriction. If somebody is asking you what is the domain of f of g, your answer will be it is entire R. All right. In this video, we have only spoken about the domain for this composition. What I would like you guys to do is to try out range for this function. Try finding range for this function and comment down here. Thank you so much, and I hope this concept must be clear now and you will be able to face any question with an ease. Thank you so much. All the best all the time.